Today's lecture is a continuation of last time's discussions, and it's actually the one that I'm the most excited about because now we're starting to get into more modern and advanced operating system design patterns. So you can see that I have OS design patterns too. Last time we talked about a few quote-unquote patterns. I mean, I suppose simple structure is a pattern, the pattern being defined by there being no pattern. But then there were a few other approaches that have been chosen by a number of operating systems, and the ones that we have listed here on the slide are sort of the prototypical examples that are used when describing these approaches. Most operating systems, I would say, that we use all the time are going to be modular monolithic kernels. I should probably be careful about saying that because the other massive number of operating system implementations we use tend to be a hybrid kernel, which we'll talk about today. It's like a microkernel, except microkernels tend to have a real problem with performance. So we also talked about the separation of policy and mechanism. This is just an overarching design goal, and you'll see that over and over again in implementations. And in fact, it makes a big appearance today. So the fundamental question that microkernels are motivated by, or that they're motivated from, is what parts of the operating system actually require kernel mode access. So you think about all the features that you might implement that you stick in the kernel, and you ask which parts of those things actually need to run with protected mode execution privileges. What stuff in the OS really requires protected execution? And there isn't a whole lot. This is actually kind of the list right here. So we need stuff that can use, or that requires the use of the CPU's privilege capability. So virtual memory management, we need to be able to control the memory mappings of processes. That requires protected mode. Okay. We need to be able to install hardware interrupt handlers so that we can dispatch based on hardware saying that it is done or ready to do things for us. So those are the kind of things we need to be able to use. So microkernels really try to keep as much out of the kernel as possible, while still retaining the capabilities of the operating system implementation. So as I say here, the kernel is only a minimal set of capabilities, and most services are actually provided as user mode processes. They are not part of the kernel proper. They don't run in kernel mode. So what facilities would that include? Well, there's this minimality principle. There's this guy named Jochen Leakey, and I wish that he was still alive, but unfortunately he died in a car accident. And he had this minimality principle that sort of guides microkernel implementation. A concept is tolerated inside the microkernel only if moving it outside the kernel, i.e. permitting competing implementations, would prevent the implementation of the system's required functionality. So you might imagine, as an example, process address space isolation. Does it make sense to have multiple competing implementations of that in one OS? And the answer is no, because if you have multiple competing implementations, then in all likelihood, implementations will not follow the same rules, and you may have easy ways of compromising the process address space isolation, and now your operating system no longer provides an important protection guarantee that it needs to provide. So that's one example. These are the things that are normally in the kernel in a microkernel. So the process abstraction, that is the ability to save the current machine context somewhere and restore another machine context onto the processor. So that's a context switch. Processor scheduling, interrupt handling, memory abstraction, so the address space isolation, management of the virtual memory mapping, the separation between kernel space and user space, and some primitive amount of inter-process communication. So if I'm going to keep the kernel as small as I can, and I'm going to require that a bunch of stuff live in user mode programs, separate processes that are running, they need to be able to interact, they need to be able to coordinate, so I need a strong inter-process communication facility. Okay, that should be pretty obvious. These are things that have to be in the kernel because it's not really possible to build them any other way. Okay, so that's our dog Rocky, in case you can hear him. Microkernels do tend to be very, very small, which is super appealing. I would love to implement a microkernel as part of an OS class, and I just haven't had the time to do that on the side so that I could build a course around it. It would be a lot of fun. Many of you may know about the operating system implementation called Minix. That's Andy Tannenbaum's operating system. Andy Tannenbaum is a professor, and he's the one that I mentioned as having the feud with Linus Torvalds back in the day. So Minix is about 6,000 lines of code in the kernel itself. Okay, so there's a question in the chat. What does the competing implementation concept mean? Well, what we're talking about is I might have different policies that I want to enact in my operating system. A really simple example would be process scheduling. I may want to change the scheduler based on the need of my users. For example, if I'm building a batch mode system and I want to be able to process data as efficiently as possible, then I want to minimize context switches. What that does is it reduces the interactivity of the operating system. So if a user were interacting with it, they'd be frustrated because the system would be trying to do as much work as it possibly could to minimize context switching. So that would yield one kind of process scheduler. Another kind of process scheduler might be more focused on maintaining a highly interactive system that makes users very happy because they feel like the system is responsive. And so being able to swap in and out process schedulers would be an example where you'd have multiple competing implementations. There's other examples, there's numerous other examples that we'll talk about as we go through, but basically it's ways of customizing the things that the OS does to handle different kinds of needs, different kinds of scenarios that you might want to support with your OS. So hopefully that'll answer the question, and if not, just keep following along and hopefully it'll become more and more evident. Now, other facilities are provided as user mode programs. So this includes things like file system implementations. You want to do your ext4, you want to do BetterFS, you want to do FAT, whatever. Those would be implemented as user mode programs that talk to hardware and expose that information on behalf of the operating system to other processes that are running that need it. Okay, so let's see. Yeah, so microkernels take this notion of separation of policy and mechanism basically as far as it possibly can go. And so anything that is a policy, you would basically build in a user mode process as opposed to being inside the kernel. Now that might seem like a bit crazy, but what this does is it yields a very robust operating system, because if a part of the OS dies and it's in user space or user mode, who cares? You just restart it. And so that's one of the things that you notice with microkernels is that they tend to be parts of OSs that handle failures very easily. File system process fails, just start it again. And you're back to a working system relatively quickly because it's isolated from the rest of the system. Okay, one little note here that microkernels have this interesting challenge that since you have user mode processes that have to interact with hardware, the microkernel needs some way of allowing a particular process to interact with a particular set of devices or a particular set of I/O ports. And so the microkernel needs to have those kinds of facilities. Okay, because now we're actually doing this from user mode instead of doing it from kernel mode where anything is allowed. So, you know, when you're writing a monolithic kernel, it's definitely easier. You don't have to think about things as carefully, but the result is also a less robust system. Another thing that I want to mention is that I gave the example of process scheduling as an example of something where you might have multiple competing implementations. And that's actually probably a terrible example because the reason why process scheduling is normally brought into the microkernel is because you need it to be fast. You tend to have, and this is sort of the x86 ballpark estimate, you tend to have about 20,000 clocks that you lose to a context switch on x86 because you have to trap into the kernel from one process who's making a system call or something like that. You save the machine context, you get into the kernel itself, you take care of whatever it is that the process wanted to do. Oh, now the process has to wait, so you invoke the scheduler. That takes time. You load the new process's machine context, and then back out of the kernel you go. And so it tends to be on the order of 20,000 clocks that you lose to a context switch. Now, if you have to do a context switch just to get to the scheduler, and then a context switch out of the scheduler to get to the next process, that kind of sucks. And so a lot of times microkernels will just go ahead and bundle the scheduler into the kernel as well, so that you're cutting down time, because everybody knows the scheduler will be run. Context switches are a reality. That said, remember the last lecture we talked about having modular kernels, where you can have dynamically loadable and dynamically linkable kernel modules. And so you could always employ a mechanism like that in your microkernel to make it easy to swap in and out a scheduler based on the system's needs. And that would allow you to achieve both the performance benefits that you want from being inside the kernel and also having the flexibility of policy based on the needs that you're trying to serve with the system. Okay, so there's hopefully some useful information to think about all of this stuff with. Here is an example of how you might build a text editor, or how a text editor might function in a microkernel type operating system implementation. And you can see, of course, you have the microkernel. There's a dotted line here that we haven't drawn, which is the delineation between user mode and kernel mode or protected mode. So the text editor, of course, is a user mode process. Take your Vim, Emacs, Atom, whatever you happen to like, and you want to load a file, or you want to save a file. So the file system itself is also going to be a user mode process. So you can see it's above that line I haven't drawn. That's the separation between user mode and kernel mode. And the disk device driver also is not in the kernel. So you have these other processes that handle these kinds of tasks. And so when the text editor wants to do something with a file, well, the way that it does it in a microkernel architecture is it sends a message, an inter-process communication message to the file system saying, hey, I want to create a new file. And so the file system driver says, okay, let me look at what path that's at. Which device is that path going to reside on? Where is that going to exist? And then it can go ahead and send a message to the disk driver. Now, hopefully you can see this seems like it will be slow, and that is the correct way of analyzing this and looking at it. Of course, you also, since these are synchronous calls, you also have the response messages coming back. So this IPC mechanism that you see in sort of first generation microkernels tends to be an asynchronous messaging type mechanism. So text editor sends a message that results in a message being sent to another process, and then those processes communicate back to the calling processes via IPC message responses. Okay, so that's cool. That seems like a reasonable way that you could build an operating system, but it's also really slow. Okay, and so as I say here on the slide, it has in the past been built with kernel level queues. Basically, you can think of the microkernel, even though it's got a small amount of code, it can manage queues, so it can potentially use quite a bit of memory. Maintain a queue for each process. And so when a process sends a message to another process, it simply puts the message in the queue for that other process. Notice this isn't the same as directly invoking code on the other process. The other process has to ask the kernel, hey, Do I have any mail? You could think of it being that way. The process has to basically say, do I have any mail? Has anybody sent me a message? So that it can retrieve those messages from its queue and respond accordingly. Okay, so it's kind of you have these little servers basically in a microkernel architecture where everything interacts. Okay, and a lot of other abstractions have been built. We'll talk a little bit about Mach because that's a pretty well-known microkernel. And Mach had the notion of creating ports. Processes can create ports, and processes can say, who's allowed to send me messages, or what privilege level must you have to send me messages, and so forth. So you could actually configure ports so that some processes simply cannot communicate with you. Or you can say any process can communicate with me. So it depends on the needs of the system. But you can see how you can create a very sophisticated set of abstractions around this. Okay, the benefits are a number, and they're huge benefits. So this is why, even though the abstraction, you may be looking at this and saying, that looks like it's going to be slow. And you'd be right. The benefits are huge. And one of them is that it's very reliable because you have a small amount of code that actually runs in kernel mode that you have to get correct. And it's pretty easy to get that correct. Also, I'm curious if any of you took Mike's proof and theorem proving course. I think it was last term. But you can actually write proofs of correctness for code, and I'm sure that all of you have seen this kind of concept before. But there are microkernels, because they're small enough, that have been formally proven to be correct. And by correct, we mean the specification and the code match. Of course, it could be that the spec is bad or something like that, but at least you can prove that the code perfectly implements the spec. There's no deviation from the specification, i.e. defects. If a service crashes, it tends to be very easy to just restart it because, what happens? Well, a process sends a message to another process. That process simply observes that it doesn't get a response message very quickly. The other process may have died and gotten restarted, and then the newly restarted process will see, I've got some messages to respond to, and the sending process doesn't really see anything in the way of failure. It can just see that there was a delay in the system's response. Okay. There is a major caveat, which is that when processes fail, it doesn't mean that state doesn't get mangled. And this is particularly true if you have a file system or persistent storage. If a process crashes in the middle of interacting with the file system, there may still be corruption. And so there's other techniques that you would have to employ to make sure that a crashing file system process doesn't actually corrupt the storage. And these techniques are well understood at this point. I mean, you've probably heard of file system journaling, where operations that are being done to the file system are stored up in a log so that if a failure occurs, the log can simply be replayed to restore the metadata of the file system back to the way that it was. There's a lot of different techniques that can be used for this. Okay, and you'll notice I have the little note at the bottom. This isn't included in the microkernel. It doesn't have to be. It's in a user mode process, and it's kind of really easy to build new subsystems in microkernel OSs because you can build that stuff in user space. It's not hard. The kernel itself is small and only does the things it really has to do. Okay, so it's pretty neat. I love it. Here's another one that's really cool. Being able to support multi-core or multi-computer systems gets really simple because all you have to do is modify your inter-process communication mechanism to support network communication. Or if you communicate via a local APIC, or you communicate via shared memory or something like that. If you start building mechanisms like that, you can easily write a microkernel OS that can run on multiple computers. And if you're curious about examples of this, look up GNU Hurd, H-U-R-D. This is an example of an operating system layer that is built on a microkernel architecture with network-based IPC, and you can have multiple computers that actually run as a single computer system. It's a really amazing and powerful approach. Yeah, so this is all I'm talking about here. Microkernel provides primitive IPC, and then you might have a particular process that's running in user mode that does IPC between other actual computers. And then the microkernel can simply forward to that process to send a message to another computer. Okay, so this made microkernel architectures really appealing at first because people discovered quickly that it's hard to write operating systems for multiple cores. So an easy way of doing it is to just keep that kernel small and lean and build a sophisticated IPC mechanism that will allow you to run on multiple cores a lot more easily. Now, there is one giant caveat, which I'm not talking about on this slide. I say here, another benefit of microkernels, supporting multiprocessor or multiple computer systems becomes very easy. There's one major component of this that's actually quite difficult, and that is if you have a threading abstraction, so processes can spawn multiple threads, and you also have virtual memory. Because a lot of times the virtual memory subsystem, like different processors, may have different ideas about what virtual memory looks like for a given process. And so you do have to build some communication into your microkernel to enable it to support multiple cores correctly. But that's a little bit beyond the scope of what we're talking about here. If you can get that little addition correct, then microkernels are a great option for supporting multiple cores. Okay, drawbacks. Well, there is one humongous drawback, and that is performance. You have all these messages that have to be passed around, and system calls are slow. I don't know how much you talk about this in CS124, but just trapping into the kernel has a certain cost associated with it because of how many steps you go through. And this was, I think I mentioned it 1 or 2 lectures ago, that this became a serious issue with the Pentium 4 processor, if we're talking about x86. And so now there's a fast path into the kernel for user programs to trap into the kernel called sysenter, sysleave, or syscall and sysret. And so just getting into the kernel is slow. So microkernels do this a lot, and that necessarily reduces the performance. Okay, first issue, message passing is an asynchronous mechanism, and a lot of times you'll notice these are synchronous call and respond type operations. So text editor kind of can't do anything until the file system comes back. So you're building synchronous interactions with an asynchronous mechanism, you're necessarily increasing the amount of times you have to drop into the kernel just to implement this synchronous operation. Okay. So yeah, this is what I'm saying here. Process A makes a request to process B, cannot progress until process B responds back to process A. So, okay, nice. That's a normal system call type operation. Yet in our approach with this asynchronous message passing mechanism, we have to do 4 system calls because we do a system call to put the message in. We do a system call to see if we got a message back. And that call can block. But then on the other side, the file system has to call into the kernel to say, did I get any messages? And it gets a message. And then it has to call back into the kernel just to pass a message back to the text editor. So that's 4 system calls now that we have just to implement this request response interaction. That's a drag. Literally, it's a drag on performance. And so, all of the other aspects of this abstraction also can become rather expensive. And I'll show you, when we talk about Mach, you can start to see some of the details of how this inter-process communication mechanism, as generalized as it is, adds a huge amount of overhead to the implementation. Okay, so Mach, I guess we're going to talk about it right now. Mach is a project that was created at Carnegie Mellon, not too surprising. CMU does a lot of innovative software and computer science research, and Mach is incredibly well known. It was implemented on top of an existing operating system called BSD. I'm sure many of you have heard of BSD. In fact, I've seen some people who are talking about BSD string libraries in the command shell. And basically, Mach was sort of bootstrapped inside of BSD by extending the BSD kernel with some more sophisticated inter-process communication mechanisms, okay, so that you could actually boot Mach and start building stuff or migrating stuff into a microkernel type approach, okay? So as it says on the slide, different parts of BSD started to be migrated out of the kernel into user mode programs that depended on this inter-process communication mechanism, okay? Sounds great, right? So we're migrating out, like it says on the slide, OS facilities are getting migrated out of the kernel into user space. Awesome. Now we have Mach 3 and it's a microkernel OS and we're super happy. The life is now full of rainbows and unicorns. Everything is wonderful. Well, so that's exciting and everybody got super interested in it, but its performance was awful. And so while everybody said, this is a great idea, this is a great concept, it's just too slow to be usable in real production systems. Okay. Now, this is where we can start to see some of the details of the abstractions in Mach, and this gives you a nice example of the types of abstractions that these systems would employ. So you have ports. A process can open a port that allows other processes to send it messages. Okay, and I have all these details here. Processes can create ports to receive messages. Processes can specify permissions on ports. So who's allowed to send a process messages, how many messages can be sent, probably details of the size of messages, and so forth. Messages are kind of like your C structs, where you can have a C struct with stuff in it, okay? And there's parts of it that say, who's getting this message, and when the process responds, where do you send the response message to? So that kind of stuff. And then you could have, these didn't have to be a single block of memory. And I think that's part of the difficulty that emerged with CMU Mach, in that the message didn't have to be contiguous. You could have it have references or pointers off to other data structures that could then be sort of aggregated together and passed on to another process, okay? And so there was this system call, Mach message. So that was a system call that was added to the BSD kernel to start migrating it toward Mach. And that would allow you to send a message through the kernel to another process or receive a message from your own queue, okay? Okay, so that's kind of promising. When you send a message, part of the, Mach message system call stated that if you are sending a message to another process, you should be able to modify the process in your own address space after you've sent it, okay? So this presents a challenge because the kernel either has to do something magical with virtual memory so that if the sending process wants to modify that message in place, that the kernel somehow presents the abstraction that it's not changing what the kernel sees or what the receiving process sees, or it's got to actually make a copy of the entire message. And that copy is going to be slow. Okay, so this is the challenge that you have. If you're going to have this abstraction that processes have isolated address spaces, you have to kind of have this rule that the sender should be able to modify the message data without affecting the message in transit. So Mach 2.5 tried to do something clever. It tried to use this technique called copy on write. So when the sending process sends the message through the kernel goes into that process's virtual address space and marks all the pages containing message bits. It sets them to be read-only, but also copy on write, so that if the sending process modifies any of those pages, the kernel gets a fault and it can duplicate the page. So it basically copies when it has to. Okay, so that's copy on write. People didn't like that. It was complicated and turned out to be pretty slow. And so basically Mach 3 went ahead and said, we're just going to duplicate the message into the kernel queue. Okay. So in Mach 3, you want to send a message. The kernel is going to make a copy of that message into some kernel buffer. And then that kernel buffer can be mapped into the receiving process's address space. So now you only have one copy, but you definitely don't have 0 copies. And what you'd really like is making 0 copies, because that's the fastest option of all. Okay. But you can see how this is a heavyweight abstraction. It's not cheap by any means to build something like this for passing messages to other processes. So this was another issue that sort of emerged from building the microkernel, which is that sometimes you'd have these different subsystems that are living in user mode programs or user mode processes, and they're independent of each other, but they actually affect each other's behavior. And that became a major issue. And so one of the examples that emerged relatively quickly with Mach 3 was the memory pager, which is the thing that decides if the kernel needs to have another physical page frame to stick into some process's address space because it needs more memory. And it needs to choose a page in a frame and evict it. Well, it's got to make a good choice. It's got to pick a page that nobody's using, because if somebody was using it and they evict it, then almost immediately you're going to generate another fault and have to reload that thing you just evicted and hopefully make a better choice the next time. So pagers are super important for the overall performance of a computer system. So so here's the premise. You can vary the pager based on your work, your working needs, and I could, we'll spend a lot more time talking about this in a future lecture when we get into virtual memory. But suffice it to say, databases are a great example because they have a lot of operations where they scan through data, which means they use each page once, and then it should be evicted. And so, you may choose a pager that tries to use your memory in a very intelligent and efficient way. So that's why it makes sense to have this in user space, so you can trade out to a different pager. But the problem is the pager doesn't have a good insight into how everything else is working and what everything else is doing because it's isolated in a process. And so the Mach pager did terribly in these kinds of low memory scenarios when the kernel was executing. So this is a problem that doesn't exist as much in a monolithic kernel because everything's in the same bucket. And the pagers there and other stuff that the pager gets affected by are in the same bucket. And so if you make a crummy pager and it starts to make other stuff break, or you make a tweak in something else and the pager starts to, make really poor paging decisions, well, it's all right there and you can tune everything at once, sort of holistically. But Mach ran into some pretty severe difficulties in this area. Okay, so that was pretty bad. So there was a fourth iteration of Mach called Mach 4, no surprise there. But unfortunately, they just could never really quite resolve the performance issues. So how did people solve the performance issues of Mach? Well, by unmicrokerneling the microkernel. They start pulling stuff back out of user processes back into the kernel. So you can see how it seemed like an appealing approach, but it didn't work out very well in the long run. So then on the scene came this individual named Jochen Liedtke. And this individual had an incredible insights into microkernels and operating system implementation. And Liedtke came up with a whole bunch of approaches that made microkernels much, much faster. And because of Liedtke's work, microkernels are now much more likely to be used in operating system implementations, because a lot of the original approaches that were slow and made everything slow were addressed by Liedtke's work. And like I said, unfortunately, Liedtke was killed in a car accident, and his work was cut short. So that was a really sad result. But anyway, the interprocess communication mechanism was where a lot of performance issues were emerging or being created. And so Liedtke created a series of microkernels. You can see here L3 and L4. I don't know what L1 and L2 were, but L3 and L4 are the most well-known microkernels. And they basically just blue skied the IPC mechanisms. They basically, Liedtke sat down and said, what do I want to do for interprocess communication that makes more sense for the way that programs work and the way that programs run? And you can see the result on the slide. Liedtke achieved an order of magnitude performance improvement, which is a big deal. Okay, so L4 basically recognizes that virtually all system calls are synchronous. So why provide an asynchronous IPC mechanism when all of our interactions are pretty much synchronous? And you can think of it as, I call a function on another process or on the OS, and the function returns, and then I can proceed. So this was really helpful, because then a process only basically had to call into the kernel. So that would send a message to another process, and then that automatically blocked the process, and the process would see the syscall return when the response message came back. So that obviously improved things dramatically. Also, L4 did some clever things with memory management. And you can see here that when process A was going to pass a message to process B, the kernel would map the target buffers from process B into process A's address space. So it could just copy them directly over into process B's target buffers. Okay, so you have one copy, and you basically always have one copy. Now you can see that these two things kind of go hand in hand, because if this was an asynchronous interaction, then you'd have to worry about, well, what if process A, does something blah, 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 blah before process B gets the message. But now you have a synchronous interaction. So you can just say, okay, I'm just copying process A's message into process B's address space, and then B can deal with it. And I won't even return until process B has responded to process A. A lot of these IPC messages are short, and especially on processors with plenty of registers, why not just pass short messages in registers as opposed to using memory and copying and bullcrap like that? So basically L4 has these fast path mechanisms for the common case. And so that resulted in a huge amount of performance improvement. Let's see, here's another one that I really love. L4 does this thing called a direct process switch whenever one process is interacting synchronously with another process. Okay, so process A says, I want to send to process B, and I want to wait till the message, the result comes back from process B. So now process A is blocked on process B. So since process A has to wait anyway, why not just context switch directly to process B without invoking the scheduler? Okay, everybody see this? So the idea is, since we know that process B can now run because it received a message and it was waiting for a message, just context switch straight to process B. We've basically fast pathed within the kernel. We don't invoke the scheduler. We don't, we only invoke what is necessary to context switch from A to B, okay? Now, this is significant, but it does have a consequence. And if you're building something like a real-time operating system, and unfortunately we didn't get to talk about that part of OS characteristics in the first lecture because I was too verbose, but a real-time OS basically makes scheduling guarantees. I need the CPU every 20 milliseconds. and the OS is considered to have failed if the process doesn't get the CPU every 20 milliseconds. So you have examples like that's an example of a real-time OS scheduling guarantee. If you have this kind of direct process switch mechanism where you're not involving the scheduler, then you may not be able to uphold all the guarantees you'd like to uphold. So that's a challenge. But for a standard general purpose operating system implementation with a general purpose scheduler like we normally use, like the one sitting in front of you, then that's perfectly fine. And you can get away with playing a bit faster and looser with the scheduler. Okay, Leakey's work was pretty revolutionary. I think these were called, don't quote me on this, you have to look it up, but second generation or third generation microkernels. So basically started making them much more feasible again. Okay. Now I do mention here that some of the L4 IPC techniques, since they start to couple processes more tightly together, it does reduce the reliability benefits. But somebody actually took, I shouldn't say somebody because it was a team. There's a version of L4 called SE-L4, where this is a version of the L4 microkernel that was actually proven correct. And again, what that means is that the code implements the spec precisely. Because it's a microkernel, you can actually start utilizing some of your formal verification techniques. So pretty cool. You can actually get close to having a provably correct operating system implementation. L4 variants are used heavily in mobile devices and in hypervisors. Those are two places where microkernels are very, very helpful. And so you'll see them in both of those places. And yeah, so you can see the list of companies there that are using microkernel, L4 based microkernels in various places. And I definitely would encourage you to search for it on the internet, because if you're interested in microkernels, there's quite a few places where you see these kinds of things. The Rust based OS Redux is also built around a microkernel approach, and I think it was heavily influenced by L4. So there's a lot of places that these microkernel approaches are being utilized. And I would love to tinker with this and have a CS124 where we do that, but Pintos is a nice basic monolithic kernel. I mean, we don't even rise to the level of modularity because we don't need to support new devices. We have a small set of devices that we support throughout the entire course of the term. So, okay. If you have any questions about microkernels, feel free to plop them in the chat. I got so excited about this, we may run out of time, but you can always review everything else on your own. So hybrid kernels are basically a response to the slowness, the performance issues that microkernels have. And so because of this, let me see, they basically believe in the ideals of microkernels, but they relax their pursuit of them in pursuit of performance where necessary. So they will migrate things back into the kernel where necessary to achieve performance requirements. Okay. So I think that's basically all we have. That's basically hybrid kernels in a nutshell. The reason why hybrid kernels are interesting is because all of your modern operating systems, except for Linux, are basically hybrid kernels. So Mac OS, previously known as Mac OS X, is built on a kernel that is based on Mach, but what Apple realized over time was there's no way we're getting the performance that we need with a Mach-based kernel. So some of the facilities are migrated back into the kernel to make it more performant. And so when we talk about memory management in XNU and Mach, like you can do experiments on your Mac that show you those details. It's quite interesting. So we'll talk a little bit about that in the future. But Mac OS definitely is an example of a hybrid kernel. Another example of a hybrid kernel is Windows. So basically starting with Windows NT, which was way back in the day, we're talking early mid 90s, But all the way up to Windows 10, we're still in the Windows NT family and tradition of kernels. This is also a hybrid kernel. Microsoft was very excited by Mach. A lot of people were excited by Mach. They built a microkernel architecture and found that the performance, as expected, was not sufficient for the needs of the OS. And so they started moving stuff back into the kernel to achieve the performance requirements that were necessary. It's too bad, right? It's a great idea, but we just haven't cracked that nut yet. We haven't quite figured out how to make it super fast. There are a few other examples, and you'll notice here I'm mentioning some OSs you've probably never heard of, but there's quite a few experimental OSs out there. And Chorus is a particularly interesting one because it basically would allow you to develop a new OS service in user mode. So it's easy to tinker with, easy to stop, restart. It can crash without bringing down your OS. And once you had it reliably working, you could co-locate it into the kernel. So that basically meant instead of running in user mode, move it over into kernel mode and run it in the same space as the kernel so that the service will now be fast and efficient and performant. So quite an interesting idea. And so you can check into Chorus if that's interesting to you. Okay, last thing to talk about is that we talked about the two basic things that operating systems do. And one of them was making sure that processes had a happy, nice space in which to live, where they couldn't trample on each other and they could be protected from each other and so forth. But the other part of it is the abstraction over the compute hardware, because compute hardware is baroque and complex and difficult to make happy. And so that imposes an overhead, a performance overhead. And so this was something that OS researchers were looking at and saying, well, that abstraction of the hardware makes things slower. Let's think about perhaps relaxing that. So you have this example here, the file system and disk files. Applications don't care how the files are managed on the storage device. They basically use this set of logical operations against logical files, and those are mapped to physical device interactions. Okay? So there's another category of operating systems called exokernels, which basically say, let's get rid of the OS abstraction layer and let user processes talk directly to the hardware. Now, obviously, this isn't going to happen in every scenario, and that's a good thing. But in situations where you see a big benefit, exokernels allow easy access to the hardware directly. So this is something that was done at MIT in the PDOS group, so Parallel and Distributed Operating Systems. And basically, the idea was an application is going to know what they need the hardware to do and how to do it efficiently better than the OS will. So instead of having the OS impose an abstraction that has costs, let's just let hardware be directly accessible by the application software. And so the OS starts to provide as little abstraction capabilities as possible. Like I say on the slide, we have the ability to allocate a portion of the device to this process, another portion of the device to this other process, or a portion of graphics memory or whatever you need to allocate. Okay, but you really don't have any further involvement between the hardware and the application than that. Okay. All right, yeah, exokernels do tend to be microkernels. They don't have a lot of stuff in them because that's up to the application now. Now, on top of the exokernel is this thing called a library OS, which basically is the thing that knows how to talk to the hardware. And so this is the mechanism now for providing abstractions on top of the compute hardware. Okay. And so applications can say, I need this libOS to interact with this hardware, and the exokernel would support that interaction. Okay, So there was the experiment that MIT did was this thing called XOS. Now, I'm not sure I like the name because MIT turned around and implemented a libOS called XOS on top of XOS. Now I'm confused. But basically, the EXOS libOS provided all of the standard Unix APIs. So this basically allowed standard Unix applications to run on top of XOS without any real change, which is pretty dang cool if you think about it. Then they created this web server called Cheetah, and Cheetah was really optimized in a lot of ways based on the needs of web servers. So if you have a web page and you think about any web page, it'll have dozens or hundreds of files that are necessary to be served for that web page. So let's put them physically together on the device so that they can be read as efficiently as possible. Not so important with solid state drives now. The TCP IP stack knew how to access the file system cache to do retransmits. So why have a separate network buffer and file system buffer if we know we're serving files? So the TCP stack would just pull data straight out of the file system cache. We're reducing copies here. And what they found in their experiment was that Cheetah was able to run 3 to 10 times as fast as standard web servers running on equivalent hardware. Okay, that sounds great. The problem is that is a really custom-built system. And I suppose it's like saying, well, of course, a Formula One car is going to be faster than, Toyota Corolla or something like that. But you don't have to be a specially trained driver to drive a Corolla down to the supermarket to buy a gallon of milk. And plus, you have a place to put the gallon of milk after you bought it. So this approach hasn't really caught on, but it's a fascinating approach. Okay, let's see. So you can look at the parallel and distributed operating system research on Exokernels. I don't think they're pursuing any projects right now in this area. You can look and see, but I'm pretty sure that this project ran its course. And there's a few other exokernels you may want to look into. There's Nemesis, which is for multimedia processing. And there's also this other one called XOMB, which I don't think intentionally started out as an exokernel, but it ended up becoming one. So, and XOMB is continuing to this day if you're interested in poking around with it. Okay, so let's wrap this up because it's almost 2 and I should have let you go already. These are the design patterns that we talked about. You will hear about a few other ones like nanokernels and other little terminology that people have come up with. But I really feel like this set of kernel architectures captures the spectrum of operating system architectures that you will see. Everything else is just kind of variants or linear combinations, if you will, of these approaches. There is one that's missing, though, and that is hypervisors. We haven't talked about hypervisors. Those are their own special universe of both facilities and implementation patterns. So hopefully, if I'm highly energetic, we'll talk about that at some point in the future as well. Okay, that's it about OS design patterns. I will see you next time.